Pulsars are a type of neutron star that emit beams of electromagnetic radiation, usually in the form of radio waves, X-rays, or gamma rays, at regular intervals. These highly magnetized, rotating neutron stars produce pulses of radiation that can be detected on Earth as they spin, similar to the effect of a lighthouse. Pulsars are of significant interest in astrophysics due to their extreme properties, which offer a natural laboratory for studying fundamental physics under intense conditions. Below is a detailed overview of everything known about pulsars. First detection: 1967 pulsars were first discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish while they were studying quasars using a radio telescope. They detected a series of extremely regular radio pulses coming from a fixed point in the sky. Initially, the regularity of the pulses led to the signals being dubbed LGM, for little green men, because of the possibility they were of extraterrestrial origin. This was the first pulsar discovered, and it emitted radio pulses every 1.337 seconds. Later, the source was identified as a rapidly rotating neutron star. Pulsars form as the result of the collapse of massive stars, typically stars that have at least 8 times the mass of the Sun. When these stars exhaust their nuclear fuel, they undergo a supernova explosion, leaving behind a dense neutron star. During the collapse, the core of the star shrinks dramatically, and because of the conservation of angular momentum, the remnant neutron star begins to rotate very rapidly. The star's magnetic field is also intensified during the collapse. A pulsar's strong magnetic field accelerates charged particles along the magnetic poles, causing the emission of beams of electromagnetic radiation. As the star rotates, these beams sweep across the sky, and if one of them aligns with Earth, we detect a pulse of radiation. Pulsars are neutron stars with extreme properties, characterized by intense gravity, strong magnetic fields, and rapid rotation. Pulsars have masses between about 1.4 and 2 solar masses, like most neutron stars. Despite their mass, pulsars are extremely small, typically only about 10 to 20 kilometers in diameter. The density of pulsars is incredibly high, similar to that of neutron stars in general, about 3.7 times 10 superscript 1 to 5.9 times 10 superscript 1 kilograms per cubic meter, meaning a sugar cube-sized amount of pulsar matter would weigh billions of tons. Pulsars can rotate extremely rapidly. Newly formed pulsars can have periods as short as milliseconds, 1 rotation per millisecond, or up to a few seconds. Over time, pulsars tend to lose energy and slow down, but many retain high spin rates for millions of years. Pulsars have magnetic fields that are billions to trillions of times stronger than Earth's. Typical pulsar magnetic fields range from 10 to 10 superscript 1 superscript 2 Gauss. Magnetars, a special type of pulsar, can have even stronger magnetic fields, up to 10 superscript 1 Gauss. Pulsars emit beams of electromagnetic radiation from their magnetic poles, which are not necessarily aligned with their rotation axis. These beams are produced by the acceleration of charged particles, mainly electrons and positrons, in the star's magnetosphere, where they are channeled along the magnetic field lines. The pulsar rotates, the beams sweep through space, and if one of the beams points toward Earth during part of the rotation, we observe a pulse of radiation. This creates the appearance of the pulsar pulsing, although the emission is continuous. Pulsars emit across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. Most pulsars are detected as radio pulsars, but some emit strongly in higher energy wavelengths like X-ray pulsars or gamma ray pulsars. Pulsars are categorized based on their emission properties and their environment. The main types of pulsars include radio pulsars. The most common type, These pulsars emit in the radio wavelength, and their signals can be detected using radio telescopes. Their periods range from milliseconds to a few seconds. X-ray pulsars. Pulsars that emit X-rays are often found in binary systems where they accrete matter from a companion star. The infalling matter heats up to millions of degrees, emitting X-rays in addition to their radio signals. Millisecond pulsars, MSPs. These are pulsars with very short rotation periods, typically less than 10 milliseconds. MSPs are thought to have been spun up by accreting material from a companion star, transferring angular momentum. Millisecond pulsars are incredibly stable in their rotation rates, making them valuable for precise timing experiments and testing general relativity. Gamma-ray pulsars. Some pulsars emit primarily in gamma rays. These are typically young, energetic pulsars with strong magnetic fields. The Fermi Gamma Ray Space Telescope has detected many such pulsars. Magnetars, a type of neutron star with an extremely powerful magnetic field. Magnetars emit bursts of high-energy radiation, including X-rays and gamma rays. Their rotation periods tend to be longer than those of typical pulsars, usually a few seconds. The intense magnetic fields cause starquakes and bursts of energy. The precision of pulsar rotation makes them highly valuable in a number of scientific fields. Cosmic clocks. Pulsars are incredibly stable in their rotation, particularly millisecond pulsars, which act as precise cosmic clocks. Their periods can be measured with extreme accuracy, often to within microseconds. This stability is used to test theories of general relativity and monitor changes in space-time. Pulsar timing arrays. Arrays of millisecond pulsars are used to detect gravitational waves, the ripples in spacetime caused by massive objects like merging black holes. Pulsar timing arrays measure minute changes in the arrival times of pulses caused by passing gravitational waves. Binary pulsars and relativity. Pulsars in binary systems, especially when paired with another neutron star or a white dwarf, provide laboratories for testing Einstein's theory of general relativity. For example, the Hulse-Taylor binary pulsar, PSRB 1913+16, provided the first indirect evidence of gravitational waves through observations of orbital decay caused by gravitational radiation. Pulsars occasionally experience glitches, which are sudden increases in their rotation speed. This is thought to occur due to interactions between the superfluid interior and the solid crust of the neutron star. Crustal adjustments. The outer crust of the neutron star may undergo sudden shifts or starquakes, leading to changes in the pulsar's rotation rate. These glitches provide insights into the internal structure of neutron stars. Spin down. Over time, pulsars lose rotational energy due to the emission of radiation and charged particles. This process is called spin down, and it leads to a gradual slowing of the pulsar's rotation rate. Death line. As pulsars lose energy and slow down, they eventually become too slow to produce observable pulses, crossing what is known as the pulsar death line. At this point, they become dead neutron stars, no longer detectable as pulsars. However, they still exist as neutron stars and may be observable through other means, such as X-ray or gamma-ray emissions from accretion or other sources. PSRB 1919+21, the first discovered pulsar, with a pulse period of 1.337 seconds. Crab pulsar, PSRB 0531+21, located in the Crab Nebula. This young pulsar has a period of 33 milliseconds and emits across the electromagnetic spectrum. It was formed in the supernova observed in 1054 AD. PSR J0437-4715, one of the closest and brightest millisecond pulsars, widely studied for its precise timing. PSRB 1257+12. This pulsar was the first to have planets detected orbiting it, marking the discovery of the first exoplanets. PSR J1748-2446 AD, the fastest known pulsar, rotating 716 times per second, period of 1.4 milliseconds. Neutron star mergers. Some pulsars exist in binary systems with other neutron stars. Over time, the two neutron stars lose energy through gravitational wave emission and spiral closer together. Eventually, they merge, creating a powerful burst of gravitational waves, which can be detected by observatories like LIGO and Virgo. These mergers also produce kilonovae, which create heavy elements like gold and platinum. Pulsars serve as vital tools for advancing astrophysical knowledge. Testing relativity. Binary pulsars offer precise tests of general relativity, especially regarding time dilation and orbital decay due to gravitational radiation. Probing the interstellar medium. Pulsars are used to study the interstellar medium, ISM. As their radio pulses pass through the ISM, they experience dispersion and scattering, providing data about the density and composition of the medium. Detecting exoplanets. Pulsar timing variations can reveal the presence of planets around pulsars, leading to the discovery of the first exoplanets. Pulsars, with their incredible precision and extreme environments, are some of the most intriguing objects in the universe. They continue to provide invaluable insights into fundamental physics, astrophysics, and even cosmology, making them a key area of study for astronomers and physicists alike.